were able to put it back together using a piece of bone from his hip, okay? And as you see, he's doing great. But if you ask him, and he's quite opinionated, he'll tell you he doesn't believe this is how people should be put together in the future, okay? Why should we be taking bones out of one part of the body and putting them in another if we injure ourselves, right? Why can't we take the cells that grew our bodies in the first place and grow a new bone in the lab? So this idea is something that I get really excited about because we're at the beginning of what I think is a real transition in history about the way that we view the body. Up until only about 100 years ago, if the body needed to be repaired, we would just kind of leave it alone and hope for the best. But somewhere around 100 years ago, when we started making machines in the factories, we started thinking about human bodies the same way. If something was broken, if you needed a new heart or if you needed a new liver, you would get one from a donor or maybe make one out of technology. But basically the idea was still the same. But where we are now, I like to call this Body 3.0, is a new kind of story, where if people get injured, they can use their own bodies to repair themselves. Kind of like viewing the cells in our bodies like living building blocks from which we can build new parts. So you might be asking yourself, how did I come to this idea? And so I wanted to show you an embarrassing picture from my childhood. We all have a picture like this, right? You're 8 years old and you get your first chemistry set and you're so happy. As you can tell, I'm from a bit of a geeky family. This is my sister Sheila, my sister Mira, me, and my brother Neil when we were children playing at a science museum in Toronto. And when I look at this picture, I see a lot of things. Because we're happy, we're doing science, but also I trace back until this time in my life what really became a very professional preoccupation for me, because my sisters Sheila and Mira are actually colorblind, and my brother Neil has a disease called retinitis pigmentosa, which leads to loss of vision. And so for me, when we were kids, this idea of how do we see the world was a very real question, because we all saw the world so differently. This idea that the reason why we saw the world so differently was very related to our DNA, right? Because there was one base pair deletion in my brother's DNA that made it so that he couldn't see at night, for example. So this idea that cells are miraculous in that they help us see was something that was very impressive to me, but also that it could be fallible like any other technology. And this is something that I began to trace through my professional career, through medicine. This is a digital theremin. Any musicians here? Yeah, a couple? Does anyone know what a theremin is? Yeah, okay, no, yes. It's a musical instrument that you play without touching it because the electromagnetic waves in your body interfere with an oscillating circuit. And I really love this exploration of human technologies interacting with our own bodies. This is me in my senior thesis presentation studying computer vision. And then I ended up actually in telecom doing communication software before I landed in this field of tissue engineering. Does anyone know this picture? It's the fountain of youth. It's an inspiration for us because as you see, people here on the left are coming and jumping into the pool and getting rejuvenated and coming out on the other side, almost like Tamarindo. But what we're really doing is we're trying to grow body parts in the lab. This is a piece of engineered cardiac tissue that I grew during my PhD work. This is almost 10 years old. And as you can see, it's beating. It's actually beating in time to an electronic circuit that I built. This idea that a circuit that you could build and plug into the wall could speak to cells that make our hearts beat every day in our bodies was something that was just very incredible for me. But after, because they told me here that you guys wanted to hear about entrepreneurship, after my PhD, I got very interested in this bigger world that was affecting us in the lab. The Bush years were happening and stem cells were controversial in our country. And I knew that I wanted to be part of the world that was affecting what was happening in the lab. And so I decided to work as a management consultant at McKinsey before coming back to the lab, actually, a couple years later to start this company, EpiBone. So let me tell you about the company. You can probably tell from the picture we are growing bones, right? It's a personalized living bone that we grow using your own cells. You might be asking, why bones, right? But after blood transfusions, bone is the second most transplanted tissue. Did you know that? I didn't know that until very recently, actually, until we started the company. Millions of procedures worldwide costing billions and billions of dollars. And the only way to get human bone is to cut it out of a human. Okay? And if you think about pediatric patients like these children with congenital defects, there just isn't enough bone to go around. We needed a better way. A lot of people ask us, as the population gets older and older, isn't this going to be more important? And yes, this is true. But what's also interesting is that people are getting injured earlier and earlier in life. And so we really need the implants that we use to replace our body parts to last more than 10 years. How does it work? We take two things from the patient. First, we take a CT scan. This is like a three-dimensional X-ray. And we get an image that we can then feed to our 3D fabrication devices. We also take stem cells from the patient's fat tissue. We take 10 ml, and we engineer a three-dimensional scaffold that matches the image from the CT scan. So we make a bioreactor. This is what we call the system that we use to grow the cells. So we put the cells and this scaffolding into this bioreactor, and after 3 weeks, we have a piece of living bone that's ready for implantation. Here's a short video. So we're engineering the scaffold, growing the cells, machining the scaffold into the right shape, growing the cells in our incubator, and this is our bioreactor, which after 3 weeks of being fed, voila, a piece of living human bone ready for transplantation, with a perfect fit and no risk of rejection because it's made from your own cells. There are so many reasons why having a perfect, like a bone that's made from your own cells, the way that we do this. Firstly, there's a perfect fit because it's made from a perfect image of your own body. Because it's made from your own cells, it will integrate without risk of rejection. And because it's alive, it can continue to remodel and grow along with you. We're very excited about this company. We've gotten a lot of really good press. And to date, we have raised $5.6 million from a mix of sources, including government grants and the capital markets. But what I really wanted to talk to you about today is how I see what we're doing with EpiBone as being part of a much broader story, because I know there are many people here who are not in the medical field. Any fashion designers here? No? Any artists? Chefs? Engineers? Yes, a lot of engineers. But we have a wide range of backgrounds, and so what I really was hoping to share with you is my joy for this larger story of how what we're doing in the lab can affect the economy. So I like this idea of body 1.0, 2.0, and 3.0. We're getting to the point where we can rethink the implants that we use to repair our bodies and make them alive. Thinking about this, but thinking about cells like living building blocks, like living Legos, actually has a much more powerful idea beyond medicine. Okay, so let's take a step back for a minute and show you a baby picture of all of you. Because you all looked like this at one point. We all looked like this at one point, right? We were all 8 cells big. And somehow we all became people, right? And many people think to themselves, I mean, everyone I know has asked themselves at some point, how did we become the people that we are, right? If you're a writer, if you're a poet, if you're an artist, if you're a scientist, this question will take different turns. But really this question of how did we become the people that we are is one that preoccupies many of us. But in our field, this particular question takes a very specific turn. How did those stem cells that we all were when we were in embryo become the muscle, the neuron, the skin, and the bone that became our bodies, right? So this is the realm of the field of developmental biology. But we are engineers, right? So we say, okay, so what? What can I do with this information? And in our field, what this means is we say, okay, what can we learn from the field of developmental biology to implement in the lab so that we can trick those cells into becoming bone, heart, tissue, liver in the laboratory, you see? So for cardiac cells, for example, we know that electrical signals are very important. So what do? When we build our bioreactors, we put electrodes in there and we paste the cells of it to grow them, right? We know with bone, it's very important for tissue to have mechanical stresses. So when we're growing bone in the lab, we implement mechanical stressors in the bioreactor, you see? So every kind of tissue needs a different kind of house. It's like an ecosystem. So as you probably have imagined, one thing that we can do with this technology is creating living implants. I showed you epibone, I showed you some cardiac tissue, but you can grow many kinds of tissue using this kind of methodology by copying nature in the lab. Now, some of the tissues are easier to grow than others. Skin is pretty easy. Anyone want to guess why? Yeah? No? Well, skin, it's simple, right? It's flat, a single cell type, right? But what about when we have multiple cell types and three-dimensional architecture and tissues that interact with other tissues, like the heart or the liver? It becomes more and more complicated. But bone is in the middle. It's a complicated shape, but we can use three-dimensional fabrication technologies to solve this problem. And it's a single cell type made from what's called adult mesenchymal stem cells. Others have grown many things. There's now a person who's been living for almost 15 years with a tissue-engineered bladder. This is from Tony Atala's group at Wake Forest. Lungs and a kidney from Harold Ott's lab at Harvard. Vasculature from Laura Nicholson's lab. But what's really interesting is if we think even more broadly than this. What can we do besides growing body parts to put into people? And if we think about this, what we're actually doing is we're growing representative systems that are like heart tissue, like liver tissue, and so on in the lab. So why not use those so that we can study mechanisms of health and disease in the laboratory as well, besides just regenerative medicine? And in the US, this is a very big issue, worldwide as well, costing so much money and time to develop drugs. Why does it cost so much money? And why does it take so much time? Basically, it's because of two questions, right? Two issues, as we would say. One is we are not rats. And we are testing in this drug development pipeline, lab testing, and then animal testing, and then clinical trials that we call human testing before we can let drugs be put into people, right? But because we are not rats, sometimes we make mistakes at this step of the process. And because of the tiny differences in DNA between all of us in the room, sometimes different drugs will affect us differently. And we don't find this out until sometimes after a drug has been approved, and that it sometimes hurts people. So how can we use tissue engineering to do this better? By growing stem cells in the lab, we can have what's called like a clinical trial, but on a chip, by growing hundreds of pieces of human tissue and testing drugs on them. So even beyond making body parts for our bodies, we can have in the lab a tissue chip that can mimic how our own bodies would act in response to drugs. This is very exciting news. And especially if we consider that we can grow not just healthy tissues, but also diseased tissues to study how diseases progress in the lab. This is an example from someone who has Lou Gehrig's disease. This is a degeneration of neurons in the body. And by engineering neurons in the lab from people who have the genetic cause for these diseases, you can study in the lab these neurons and hopefully find cures faster. This is another example from retinitis pigmentosa, the disease that my brother has, and we hope that models like these can help us find a cure someday. This is an example of 3D printed cancer cells from Karen Berg's lab at Clemson University, 3D printed breast cancer cells. And there are labs that are starting to combine these different kinds of tissues on the same chip so that we can study how drugs that affect the heart might be affecting the liver and so on. But what even broader than what's happening in the field of regenerative medicine and these tissue-on-a-chip systems, what I think is really interesting, especially to a wide audience like this, is to discuss how much biology is not just in our field, okay? How biology is creeping out of the lab and cross-pollinating across so many fields around the world. So I know no hands went up when I asked if anyone was a fashion designer. Anyone want to change their mind? A couple, maybe one person is shy. This is my friend Suzanne. She's a London-based fashion designer, and she is growing, it's like, she calls it vegetable leather. She's using, it's almost like kombucha. She's using, you know, this tea with like sugar, yeast, and bacteria to grow vegetable cellulose. And she's put them in everything from shoes to leather jackets, okay? This is the power of biology. growing leather without killing animals. Asking the question, what can we grow out of cells instead of building using traditional machinery? You see? This is my friend Mitch Joachim. He's an architecture professor based out of NYU, and he asked the question, why are we building homes when we can be using trees to grow homes? And he's been experimenting with growing living lattices of trees to help, that can someday be used as prototype walls. Meet Andras Forgacs. He's the CEO of a company called Modern Meadow based in Brooklyn, New York. And he asked the question, why are we growing fields of grass to feed the animals that we then use for meat and leather? Why don't we just grow the cells and make meat and leather in the lab without ever having to hurt an animal? This is my friend Damien Palin. He's based out of Singapore. He's a biomineralogist, and he collaborates with bacteria to take the salt water out of salt water, take the salt out of salt water, and mining salt water for minerals. So generating wealth from waste while helping to save the environment. Given how much little water there has been in Costa Rica lately, these kinds of techniques will be very powerful when we try and think about forces that are affecting our environment, like lack of rain in the rainy season. But any game designers out there? No? Oh, 2 people. Okay. This is Ingmar Rydell Cruz. He's a bioengineering professor at Stanford, and he was actually a physicist before that. And I showed you the cells of the cardiac cells that were beating, right? What he did is that he was playing with bacteria and paramecia specifically that respond to electrical signals. Now, they don't beat when they are put in electrical signals, but they swim towards the direction of the negative electrode. And so what he did was he hooked electrodes up to a joystick, and he made a video game in which paramecia are playing with the pixels on the screen. Watch the video. You can see the ball is interacting with the microbes to destroy the rocks. And on the other end of the design spectrum, this is Jae-Rim Lee. She's an artist who developed a particular strain of mushroom called the infinity mushroom that she incorporated into a bodysuit that can be used as a kind of living coffin to remediate the toxic byproducts that are released by the body after death. And right now, there's a man named Dennis who's actually raising money for the first eco-funeral ever to be held. Questions like, how does the way we choose to die affect how we choose to live? You might be asking yourself, what else could we do, right? This is almost ridiculous. And I wanted to say, well, I love this quote from Anton Chekhov that says, the role of the artist is to ask questions, not answer them. And I wanted to show you some beautiful work from the field of bioart. That's Yonat Zur and Oran Katz. They saw that picture of that mouse with the ear on its back and said, we want to grow tissue engineered systems so that we can grow art out of them. And they're very ironic. So they did things like, said if pigs could fly, what would their wings look like? And they grew wings. And they grew in the Museum of Modern Art in New York City a tissue engineered leather jacket. It was called the victimless leather jacket. And one more project I wanted to show you from their lab is a portrait here, which maybe you can see in this petri dish. It's a piece of, it's a portrait that's drawn from bacteria that has been transfected to glow red. And at the same time, it was transfected with a piece of DNA that's been implicated in human Alzheimer's disease. So as this portrait fades over time, it evokes this idea of lost memories in a way that you could argue very few pieces of art really could. So what's next? I hope that I've introduced you to a lot of crazy technologies that are coming online. Everything from art and architecture to biology and design. But what I think is more important to ask, what can we do with biology? It's more important to ask, what should we be doing with biology? And so I think it's very important to remember that every time that we have disruptive technologies that come into our civilization, we have to think very carefully about how we want to use them. This is an example from the telegraph from about 150 years ago. We had everything from online shopping to social media back then, and we got through it. And many of the questions we're asking now with regards to human identity, as with stem cells and with embryonic stem cells in particular, a lot of these questions we were asking ourselves when we started doing blood transfusions only 100 years ago. So what I like to advocate for is for everybody to learn how to do some biology. Has anyone here ever taken DNA out of a strawberry? No? Look it up on YouTube. You have, yes, in the back. It's so much fun and it's so easy. So you just look it up on YouTube, okay, I promise. You take strawberries, soap and water, and you smush them up in a Ziploc bag, and then you pour them through a coffee filter, and then take Bacardi 151, very, very cold, and out pop it, you pour it in and out pops the DNA. It's so amazing to see it come out of the strawberry, right? And what's really cool about this is that many times people don't realize that DNA takes up space. DNA can be held in your hands. The code that tells every cell in our bodies to be human and tells them how to create our bodies is actually inside us, right? It's computer code that you can see. Anyway, my theory is that if you touch DNA and hold it in your hands, bioethics discussions will never be the same. And so I want everybody, in the future, like in 10 years, if I'm back here and I ask, has anyone taken DNA out of a strawberry? I want every hand to go up. So I teach people how to play with biology. These are 3 architecture students that we are growing skin together. And this is an artist I'm working with, Maya Yoshida, who was taking the CT scans from the bones that we were growing in the lab and making jewelry. I think it's very important for us in the medical fields to collaborate as widely as possible so that we can make sure that the technology is in our society in a good way. So they asked me to finish up with some, not just advice about the technology, but any words of wisdom. So in my last few slides, I wanted to just share some thoughts that I've had over the years from building this company. Firstly is I think it's very important for all of us to be curious, to follow our passion and run in that direction. I think it's important for us to be honest with ourselves about our own skills and honest with ourselves about what we want to accomplish. And that a little kindness goes a long way. Time flies. Paths often wind. I just came from 1 week surfing, and the ocean will teach you that everything is always in motion. And find your soulmates. If your dreams are bigger than you are, always find your tribe. These are my classmates from my MBA program, and there are investors, my insurance brokers, and so many mentors in this picture. So if you look to your left and if you look to your right, you are the people that are going to change each other's lives, and never forget that. Try not to give up your hobbies, and remember that every path that's worth taking requires patience, like our friend the sloth here on the colones, 10,000 colones. So thank you very much for your time. Thank you for your patience with my late arrival, and if you have any questions, I'll be around. Thank you very much. Thank you. Thank you.